Good afternoon, ladies and gentlemen, and welcome to Chapter 11, Vibrations and Waves. First thing we're going to do is talk about springs. So you're going to be learning about simple harmonic motion and Hooke's law. Okay, so I just saw a spelling mistake. There should be an E there. Hooke has a silent E. Okay, so we have different kinds of springs. Some have energy stored when you stretch them. And you guys should have gotten your springs in the mail. If I hang, I'm going to put it here, and if I hang something to it, a mass, it's going to stretch. How much it stretches depends on its spring constant. Now you'll notice that the British say, it's on your lab, what it's called. We say in the United States spring constant. I think they call it elasticity something. So how elastic is it? Is it really tight? I have one here that's tighter. This one requires a lot more force for me to stretch out. Oh, you'll have to believe me that I'm pulling really hard. It's not hardly moving at all. So I can move it up closer to the camera. Oh, no, it's out of focus. All right, and then some springs have energy stored when you squish it. So maybe you've played with some toys that had a spring in there. I'll be getting you guys a spring scale to show you an example. Whoops, that one went flying. So when you push it, you're going to store some energy, and as soon as you let go, boing, it jumps right out. Okay, so depending on that delta X, the displacement we're going to call it, how much did it get stretched out or how much did it get smushed in, and the force. So we have a relationship of the force of the spring is equal to the spring constant. That tells you how hard or easy it is to stretch it out or push it in, and the distance. So X is actually the distance. All right, so here's an example. I've got a mass that I hung on to this spring and how much it stretched out that distance. So from here to this one, we got stretched out X. So to find the spring constant would be how much force was it, and what would the force be of the mass? mg, whatever the mass is, times little g. Negative 9.81 meaning it's pointing down. Okay, so we're going to take that mg and divide it by the distance x, and that's how we'll get our k. All right, again, I don't want you guys to get hung up on the signs because really we're talking about what the magnitude is. Okay, so if the force is negative and the x here is going to be, then you're going to see this with your homework. All right, here's twice the amount of force, and we went twice the amount of the distance. Okay, all right, so that's the first thing we're going to be talking about. There's my little examples of your springs, and you guys have one too for your lab. You'll be stretching out that spring using your cell phone in a little baggie. Okay, so there's our equation. Now let's look at the problem of practice A, preparation for practice A. Here it is. Janet wants to find a spring constant, so that's that K of a given spring. So she hangs the spring vertically and attaches a 0.4 kilogram mass to the spring's other end. If the spring stretches for 3 centimeters from its equilibrium position, what is the spring constant? All right, and spring constant is going to be newtons per meter. Newtons per meter is the units. So let's take a look at that problem. I write it down here. I set it up here. All right, so what did it say? It said that when it was stretched out, it was 3 centimeters. So here's my little spring with the mass, and when it got stretched out, it was 3 centimeters. And it said that the mass is 0.4 kilograms. All right, so if I were to do a free body diagram for my little mass, I have just the mass by itself. I have mg pointing down. Well, I know that mg must be, that's the force due to gravity, is equal to 0.4 kilograms times 9.81 meters per second squared, and that would give me newtons. Okay, so I know that that's my force. And what is the equation for elastic force? Is equal to this negative spring constant times the distance. Okay, the spring constant times the distance. So here they're asking for what is K? We want to know what K is in this problem. Okay, so as you know, I want you to solve for the variable always. All right, I'm going to divide X to both sides. My X cancels out. Okay, so I'm going to put a negative on the other side there. Multiply -1 to both sides. All right, So now I'm going to have negative the elastic force divided by the displacement is equal to the spring constant. All right, and we already noticed over here, I've got a negative, this would be a negative 9.81. So this is equal to a negative times 0.4 kilograms times negative 9.81 meters per second squared. All that divided by, okay, now this gave it to me in centimeters. And I told you that, put here, the units for K is always newtons per meter. And that means how many newtons did it take you to stretch it out? A whole meter. Okay, so we need to have it in meters, and they gave it to us in centimeters. No problem. See over here, I'm going to change that. I can do it down here too, but let's do it over here. 30 centimeters. I know 100 centimeters is to 1 meter. I'm like, oh, that's right. I just need to divide it by 100, which means move the decimal place over by 2. That'd be 0.3. So this would be 0.3 meters. Okay, so upstairs here I have newtons, and it'll be newtons meter, which was what K should be. Here is my calculator. All right, so let's do that. I think we were zoomed in maybe a little too much. Okay, here we go. So I have clear 0.4 times 9.81. I can remember. 0.4 times 9.81. There we go. And divide that by 0.3 because it was 30 centimeters. Oh, you know what? I didn't move it over 2. Was it 3 centimeters? It would have been 0.03. I apologize. 0.03. So moving over to 30, it wasn't 30 centimeters, it was 3 centimeters. 3 centimeters. I move that over and it's 0.03. All right, try this again. 0.4 times 9.81. And it's all in order, so it's okay to divide it now. 0.03. There we go. And I have 130.8. So K is equal to 130.8 newtons per meter. Okay, newtons per meter. All right, and if you're worried about significant figures, then it would just be 2 significant figures. We'd say 130 newtons per meter. Okay, you know, I'm okay with you guys giving it to me like this. All right, but here it is with 2 sig figs. So very basic on knowing the equation of your elastic force is equal to the negative spring constant times the displacement. The displacement, how much did the spring get squished in or stretched out? All right, so that's the first one. Let's go to the next one, which is number 9. In preparing to shoot an arrow, an archer pulls the bowstring, I don't know if it's bowstring or bowstring, back 0.4 meters by exerting a force that increases uniformly from 0 to 230 newtons. What is the equivalent spring constant? So I don't know if you've ever had a chance to play with a bow and arrow. I did in Girl Scout camp. All right, so you have a bow and arrow. And what you're going to do is you're going to take this stiff part, sort of stiff, and you're going to pull it back. You're pulling it back. And here's your arrow. So how much you pull back, what happens when you let go? It's going to want to straighten up again. Okay, so that one's similar to this spring. No, not really. More similar to this one. Again, I'm stretching it out. As soon as I let go, boom, it goes right back. So it tells us, let's see what it tells. It tells that the displacement here, when it pulled it back, displacement was 0.4 meters. All right, 0.40 meters. Yeah, right here, 0.40 meters. All right, 0.40 meters. And they told us that the force was from 0 to 230 newtons. So it took you 230 newtons to finally get it right before you're going to let it go. So that's the force that we're going to take. All right, so let's write our equation again. I have my elastic force is equal to the spring constant times the distance. And again, I want to solve for the spring constant. So I have K is equal to negative of the force divided by the x, the distance. All right, so I pull it back 230. I'm pulling it back, and the distance could say negative. Again, I want you guys to realize that a spring constant does not have sign. Okay, so no matter what, it's always going to just be positive. So we're just going to take the 230, because you're pulling it back. You could say that was 230 newtons. Either way, we want the magnitude, 230 newtons, and we get the distance, the displacement, and good. I know that I'm doing it right because I get the units of newtons per meter. All right, so let's see, I'm moving here paper. That didn't help, huh? Okay, here we go. 230 divided by 0.4. And we get 575 newtons per meter. 575 newtons per meter. Okay, and then if we look and we go, oh, wait a minute, I only have two significant figures. Oh, so this would have to be rounded off to 580 Newton meters. Fine. I'm okay with either one. All right, so that's all I have for this one here. On the next one, I will do for practice B. Okay, see you next time.